So, welcome everybody. Harvard says the speaker is allowed to take their mask off as long as they stay far away from people, so we will be practicing that. As you all know, 2 years ago we suddenly stopped the ITC lunches and have not had one since. This year we're starting again now. We'll do it this week, not next week because of spring break, and then we'll try to do it every week after that for a while. So the honor of the first ITC lunch talk in 2 years goes to Karin Oberg, professor of astronomy here and our director of undergraduate studies. She studies astrochemistry and especially its impact on planet formation using a combination of lab measurements and ALMA types of millimeter data, and of course theory. So Karin.
Thank you, Doug. So it should then be no surprise that I will be talking about chemistry and how it affects planet formation for the next 10 minutes. But I do want to focus on what I think is sometimes seen as a slightly more complicated part of the chemistry, which is the organic chemistry that we find in these disks of dust and gas around young stars where planets are currently assembling. And there's sort of three reasons that at least I like to study the organic chemistry. So this is the sort of carbon-based chemistry in these disks. One is that these are also the disks where potentially habitable planets are assembling. So if we're thinking about setting the initial organic inventory of planets, we want to know what kind of organic molecules we have in these disks. But also it turns out that the composition of this organic material that we can study with telescopes such as ALMA seems to be very sensitive on the elemental composition of the gas in these disks. So we could potentially use these organic molecules as tracers of the elemental composition of the gas, and we want to know the elemental composition of the gas because that determines the elemental makeup of planets, such as their carbon to oxygen ratio. There's a third reason, which is this bottom here, which is that the chemistry that happens in these disks will affect where the reservoirs or repositories of carbon and oxygen are. And there are several mysteries that's related to that. One is that when we study these disks, there seems to be a lot of oxygen missing, which we're not entirely sure why. Maybe some excess carbon, which we don't know exactly where it's coming from. And if we're looking at our own solar system, there is a lot of carbon missing in the inner part of the solar system. Now, the reason I want to bring in sort of three topics into a 10-minute talk, which of course is not necessarily something I advise either me or other people to generally do, is that it turns out that they're intimately connected. And that's what I'm going to try to convince you of. But let's start with the first one. So trying to understand what's the initial organic inventories of planets and how that could affect origins of life chemistry on those planets. There are several sort of pathways towards the building blocks of life that actual chemists, not astrochemists, have come up with. The one that I find the most compelling is the one that's illustrated here, where you start with hydrogen cyanide, some small sulfur molecules, water, and UV light, and you end up producing quite readily all the major families of biomolecules that we have here on Earth. The reason one might suspect that the astrochemical inheritance might play a role in this chemistry is that the molecules that are involved, and especially hydrogen cyanide that's at the heart of it, are the same kind of molecules that we know were common in our own protoplanetary disks. We see them in comets, and that one might suspect are available where other planets are forming. But of course, you don't want to just suspect. You want to actually see what kind of chemistry is available where exoplanetary systems are assembling. And the main telescope that we have been using up to now to do that is ALMA, this beautiful interferometer in Chile, which allows us to not just see if a molecule is present in one of these young disks around the young stars, like the disks around the young stars, but also map out where the disks are. So I mean, the big advantage with this kind of interferometer is that they give you really exquisite resolution. And if you then can isolate the photons that's coming from a particular molecule, you can make images of where molecules are. So this is something that some of you have seen before, but we spent a large portion of the past couple of years taking those kind of images of different molecules towards 5 protoplanetary disks that are here shown in their thermal emission within the MAPS program. And this is showing some of the data that we took, where now each row is one of the disks and each column is a different molecular line. So this is a very rich data set, and for any of you who have not seen any of the MAPS papers, definitely invite you to have a look at them. But the main thing that I want to focus on is that most of these molecular images are images of organic molecules, their distribution in these disks. And I'm just showing an example here towards one of the disks. 4 out of the 5 images are organic molecules. The bottom line just shows the radial distribution. The main point then is that there are lots of organic molecules commonly present where planets are assembling. And if we try to estimate their abundance, especially of this hydrogen cyanide that was implicated in the origins of life chemistry, we get abundances that are sort of intuitively pretty high in the sense that we have things like percentage abundances compared to water, water being the most abundant constituent, both in comets, but also in these disks, we think. And if we compare it with the best evidence we have of what our own disk was like, which comes from comets, so that's this gray shaded line, we see that we have a very similar kind of organic molecule abundance in these disks forming exoplanetary systems compared to what we think our own disk was like when the solar system was assembling. So this is pretty encouraging. It suggests that planets typically form in very organic, rich environments with the right kind of organic molecules present. But as I indicated, it's also telling us something about the elemental composition of these disks. This is an image of the molecules, the organic molecules that have been detected in disks so far. The main thing I want to point out here is oxygen is red. Most of the organic molecules we're finding are oxygen poor, especially this group here, the blue ones. These are so-called nitriles, nitrogen-containing organic molecules are very common. What this is already sort of qualitatively suggesting to us is that the gas is pretty oxygen poor. We're finding so many more of these carbon-rich, like lacking oxygen molecules compared to these oxygenated organics. We can look at this a little bit more quantitatively, like what it means to be sort of surprisingly oxygen poor, by considering what we would expect in the simplest model of one of these disks, which is that we have some inherited abundance of volatiles from the previous stages, and then we divide those between the gas and the solids based on the temperature of the disk. And what you would expect then as you step away from your star is this sequence of snow lines where some volatile goes from being in the gas to being in the dust. And at each of these snow lines, you will change your elemental ratio in the gas because you're moving some of the oxygen into the solid or moving some of the carbon into the solid. So if we take our typical idea of what this initial volatile composition is, just from the interstellar medium, I'm showing it here for oxygen, carbon, and nitrogen. The main point is that the carbon is roughly divided into carbon monoxide and into carbon grains. And carbon monoxide doesn't freeze out very easily, so it's going to be in the gas phase throughout most of the disk when everything else has gone into the solids. That gives you a carbon to oxygen ratio, sort of maximum in the disk of unity. So this is enhanced carbon to oxygen, but it's not like super enhanced. It's like you have the same amount. If we compare that to what the abundance of organics, these oxygen-poor organics in the disks are suggesting, and that's what's shown here on the y-axis, just the column density of this one organic, C2H. I could have put any, basically, of the organics we see almost on the y-axis. On the x-axis, it's just the radius in the disk. And then you see the observations in black and then different models assuming different carbon to oxygen ratios in the colors. The main point is that you need to get to very high carbon to oxygen ratio well beyond this unity to actually start reproducing these abundances. And this is confusing because we don't have any other sort of carbon reservoir to pull from. We had CO and we had this carbon dust. So what's going on? And what I would suggest could be going on is basically one out of two things, or maybe both. One is that we are converting a lot of our carbon monoxide into some really sort of heavy refractory organics that's moving somehow more oxygen than carbon out of the gas phase. And we do see some pretty oxygen-rich organics in comets, for example. So this cannot be ruled out. But the models we currently have suggest that this is not efficient enough, this sort of chemical conversion of the initial reservoir. Our other option then is to take some of our refractory carbon and bring that into the gas phase. That would be another way to change our carbon to oxygen ratio. And I would say that it's not clear how you could actually do that, but we think that somehow we're going to have to do that. And that might then tie back to one of the mysteries of our own solar system, which is that a lot of this reservoir, this refractory carbon reservoir, it's missing, basically, from the inner solar system. And there's no reason from sort of a thermodynamical point of view that it should be. So I would say this is currently a frontier to figure out how do we get some of this into the gas phase that then changes the elemental ratio, therefore the elemental makeup of planets. And it also seems to be driving this very rich nitrile chemistry that's then setting the organic reservoir of planets. And with that, I am done and happy to take any questions.
Can you tell us some ideas for what would drive the refractory grains into the gas phase?
Yeah, so there's a couple of different ideas. These disks, even though I didn't talk about it, are dynamical objects. One could imagine a sort of sorting between the oxygen-rich solids and the carbon-rich solids. And this is sort of for two reasons. One is that you could, this is something Diana Powell and I are actually working on. They are expected to have different size distributions when the disk begins. And that means that one of them might be better coupled to the gas and one reservoir might be drifting more through the disk. Another possibility is just that you have an initial sort of raising of all the solids sort of up to the surface of the disk through some sort of dynamical process. And the carbon grains end up being much more sort of vulnerable to chemical attacks from atoms than silicate grains are. And maybe it's a combination of both, but those are some ideas. But it is not, let's say, quantitatively, this is far from a solved problem. Dimitar.
So Karin, as good as the observations now are, they actually blind to the inner 1, 2, 3 astronomical units, aren't they? So once you can see that in those disks, do you expect any surprises along those lines?
Yeah, so there are two things they're blind to, so thank you for that. One are the innermost regions and all the solids. So we're only tracing now the gas and other parts of the disk. James Webb should help a bit with both. It will give access to that innermost part of the disk, and in theory, in some disks with a favorable configuration, to look at the ISIS in absorption. Yes, I would expect that we should see that inner part, the solids, to be carbon poor, and that we therefore need to see a lot of that carbon in the gas phase. Now, whether we're therefore going to see a high carbon to oxygen ratio is actually a little bit more difficult to predict, because we also expect a lot of the water ice to be sublimating in the same region, so that there's not as clear cut as it is in the outer disk, where all the water should be gone, and we therefore get these very high carbon to oxygen ratios. But it's going to be really exciting to see what James Webb reveals there.
I just had a related question, which is, does the change in the properties of the grains, the size, distribution, shape, et cetera, we don't know that much about that, and could that explain some of the chemical processing?
Yeah, no, it's a good question, and we don't know very much at all. Like, we have some constraints, which is that a lot of the grains have grown and seems to be settled towards the midplane, but we also still maintain a large fraction of these smaller, perhaps fluffier grains that get elevated throughout the disk. And you're right. I mean, I think, like, especially with these carbon grains, we don't really know what they're doing. We're hoping that we can get them to circulate to release some of this carbonate gas phase. What we also don't know very well is that once you get bare grains like close to the star, you have this high temperatures bare grains, that chemistry is relatively unexplored. I think we understand more about sort of the icy chemistry further out. So there are lots of sort of grain-related mysteries. And also, I think even what you're starting with, once you get to a disk, you have already gone through a sort of pre-stellar cloud core phase and a protostellar phase where there also would have been some grain evolution. I mean, you have high enough densities there. And currently, most models sort of start assuming sort of interstellar cloud kind of grain composition rather than taking into account that sort of pre-existing grain evolution. So, yeah, I think lots of questions.
All right, thanks, Karin. Okay, next presenting is Eric Kosh, who's an SMA postdoc here. He works on star formation from the scale of stars all the way up to whole galaxies and looks at atomic and molecular gas in nearby galaxies using radio and submillimeter data. And he develops and maintains tools such as spectral cube fill finder and Turbusent. Eric.
Thanks for the great introduction. So I realized I have a really terrible habit of staring at my slides because of how many virtual talks I've done. Not to stand like this. We'll see how that goes. I'm really excited to share some of our results looking at these two galaxies in great detail. So the northern half of Andromeda and the entirety of M33 or Triangulum. In particular, what I want to highlight is that we now have a lot more information about the atomic ISM.
Sorry, we're miking the speakers here, so forgot about that part.
Doug, can we just change the lighting? This is for like when you want to illuminate lights.
Yeah, sorry, how did we get in that lighting mode?
Perfect. Wonderful.
Did that do it?
Yeah.
Okay. I'm not ready. Back away.
All right. I want to highlight that we now have a lot more information about what is going on in the atomic gas beyond the Milky Way and Magellanic Clouds, where we've typically been limited before. And what I want to especially highlight and leave you with a couple open questions is that with this extra information, there's this rich area for comparing simulations to observations, in particular doing so with synthetic observations. And so what I mean by that is taking a galaxy scale simulation or parts of a disk, typically in post-processing, doing radiative transfer to mimic a particular line, and then adding observational effects, the spatial and spectral resolution, the sensitivity, but especially for high-resolution data like this, all the things that an interferometer can do to your data. And so to back all the way out, and why do we care about studying the atomic ISM on these galaxy to local scales, is we can look at this beautiful movie made by the TNG collaboration focused on this one galaxy as it evolves in time. And what this is really highlighting is the critical role that the surrounding environment plays in the evolution of these galaxies. And so one of the really crucial roles that the atomic ISM can play is trying to link these large scales, the surrounding environment, down to the scale of the disk, and to the size of molecular clouds where the next generation of stars will form. And so in my talk today, I'm pretty much just going to focus on this sort of disk scale and smaller, but in general, it's this much larger picture that we want to be trying to put together to better understand the baryonic cycle. And so this is especially important for the atomic gas in the galaxies that we can actually resolve these scales, which is the redshift 0 universe, simply because it's the atomic gas that's the dominant component of the neutral ISM by mass. So if we want to understand what's going on in the disk scale down to the much smaller scales, we really need to understand what's going on in the atomic ISM. And one of the long-standing difficulties in doing so is that there's a large range in physical environments that we expect the atomic ISM to inhabit. And I'm sure this is something everyone has heard about, but this is coming from this long-standing idea of the two-phase ISM, which we know isn't quite correct, but it's sort of the cartoon value, hence the two-ish phase. And so I'm showing here different phase diagrams. That's temperature on the top, pressure on the bottom as a function of density. And that solid curve is the equilibrium between heating and cooling processes in the atomic ISM. And so what's been long recognized is that there's a range in pressures where you have multiple stable equilibria in pressure. And there's the diffuse warmer component, that's the warm neutral medium, temperature is 6,000 Kelvin or so. And the cold neutral medium is much denser, and temperatures around 100 Kelvin or so. And much of what we know about this observationally comes from basically just within our Milky Way. Because we can make these comparisons, this is showing the 21 centimeter line in two different views, of what we see in emission from this transition and what we see in absorption on the bottom. The absorption is primarily just a function of the opacity, and so that almost uniquely traces only the cold neutral medium. So it tells us where the cold gas is. The emission, on the other hand, is a little bit more tricky because it's some combination of both the warm and the cold gas. And so we can do this fairly well within the Milky Way because there's basically atomic gas in every direction within our place within the disk. And so you can pick your brightest background sources that you can look at to try to measure this absorption component. And so spatially what we are typically looking at is, this is the same 21 centimeter line tracing the atomic ISM in two vastly different views. What we see in the Milky Way in absolute great detail, and that we understand a lot of the atomic ISM physics from, but due to its sort of ubiquity in the galaxy and its complexity, it's hard to understand how that sort of fits into the much larger scale role of the Milky Way. We can, of course, get this much easier to understand view, which is to go to nearby galaxies where we can easily understand what is the distribution of atomic ISM within that galaxy, but we give up a lot of the details, both the spatial and the spectral view. And so we typically look at images, but for the kinematics in the results that I want to show, it's much more helpful to look at what a representative spectrum is like. So this is the same view, but now in terms of spectra. We have the Milky Way on much smaller scales. And when we look towards the galactic plane, we get these enormous wide components as we trace different distances along the Milky Way's rotation curve. And again, we can trace the cold gas almost uniquely by picking locations where we have a bright background source to measure the absorption against. We're far more limited when we leave the Milky Way. This is what we typically see in nearby galaxies. They're much smaller areas on the sky, so we tend to have very few lines of sight that you can measure that absorption against. And we're very limited on the sensitivity. So this is still really fantastic data. This is just a limitation of radio interferometers that we currently have. And so what I want to show in this talk is that we can start to fill in this gap by looking at our local group in really great detail. And so this is showing some of our new data. And qualitatively, what I want to impress upon you is that this middle view is getting towards the complexity that we typically see in the Milky Way, as opposed to this sort of one component that we see in nearby galaxies. And so to give you a sense of the data that we're looking at, I've made this 3D volume rendering. So this is a position velocity cube. So each pixel, spatial pixel, has an associated spectrum with it. And we can get a good idea of what this data actually looks like. There it goes. So I've tipped from the spatial dimension so that the velocity dimension is now roughly in the y-axis. And as it spins around, what you can primarily see is the galaxy's rotation curve. But there's also a lot of small-scale detail within this map as well. And so a lot of that is coming from, and as you can imagine, these are very well-studied galaxies. That detail is coming from a very high spectral resolution coupled with a high sensitivity. So essentially, taking a really long observation of some of these targets. This is important as we were comparing that warm and the cold atomic gas, because at 400 meter per second channels, we can resolve the thermal line width that we expect from that cold gas. So in theory, we can recover the sort of the full range of expected line widths. It's a little bit more helpful if we go back and just look at what some individual spectra look like. And so I'm showing here just a sample of what we see in M31 and a sample of what we see in M33. And basically, everywhere that we look, the spectra has some sort of complexity. It's not just sort of the single broad component. There are many different details in this. And so that begs the question, how do we start to interpret these spectra and better learn about what that's telling us about the underlying atomic ISM? And so one of the things that we can ask is, when we have access to this information, what happens if we apply the methods that we're typically more limited to in other nearby galaxies where we have a lot less information? And in particular, the results I'll show today are mostly looking at one parameter, and that's the width of these lines, because this informs a lot about what we know about the atomic ISM in these galaxies. And so the width of this line, the line width, is some combination of the thermal broadening plus a turbulent component. And so it's typically assumed that if things are beyond what we'd expect from just the thermal line width, everything in excess has to be some sort of turbulent energy or something driving that extra turbulence. And so what we did in M33 is we simply compared different methods that are used in the extragalactic H1 literature to measure this one parameter, just the line width. And so this is the line width on the y-axis as a function of the galactic centric radius. So each point is sort of over these azimuthally average rings. And it's the exact same data, just using 4 different methods. And we have this scatter of almost a factor of 2. Each of these points does actually have an error bar in it. And so this is simply coming from defining what the width of a line is in different ways. And because we typically interpret the excess from the thermal line width, so for the warm gas, that would be about 6 kilometers per second, because we interpret that excess as coming from some turbulent energy source, we get this really large scatter if we compare the turbulent energy dissipation to different sources for that turbulence. And so in the solid line, this is just different mechanisms that we expect. The solid line is supernovae. The dashed line is magnetorotational instability. And so what's interesting about this, and I think a really important role for synthetic observations, is that our data is now good enough that it's overcoming the methods that we've typically been limited to before. And so if we want to be able to do a better job, we need to understand what are the biases that are coming in with these different methods, because improving them is going to shrink that gray region down, and we can make a much better connection to what is actually the underlying source of turbulent motion in the ISM. So if some of these methods start to break down where we are typically limited in the data or the information that we have, the next step is to try to do a better job modeling. And so if it's not one blob, well, maybe it's multiple blobs or multiple Gaussians. And so we can do this long procedure that I won't get into the details here of splitting these into some number of Gaussian components. This typically works. You can see the one in the top left. Those are very well-defined peaks. But as we look in the top right here, some of these Gaussians really start to blend together. And if you've ever done this with multiple Gaussians, you'll know that they're correlated parameters. You don't have a unique solution, and so that there's some matter of actually interpreting how this connects to the physical ISM that it's tracing. But what we can look at instead is, instead of the line widths I was showing before, average sort of spatially using the entire spectrum, we can break this down into individual components across both galaxies. So this is a normalized PDF as a function of the line width. And I've split this into a few different ways that I'll get into in a second. But you'll notice on the x-axis, there are extremely large line widths that we're apparently recovering, far in excess of sort of 10 kilometers per second. And so taking that at face value, that would mean it's extremely turbulent. That's hard to sort of physically interpret. But what we can do is we can split these into the parts where those components are really blended, so they're correlated parameters, so they're not necessarily unique. And that's the majority of these really wide ones we see here. And the ones that are really distinct, where we can kind of trust the widths of these individual components a little bit better. And the interesting thing with these individual components is that we're now finding that the majority of them are less than 6 kilometers per second, or less than the thermal line width that you'd expect just for the warm neutral gas. And so instead of saying that most of the medium is supersonic, that's suggesting it might be more transonic or subsonic turbulence across most of these galaxies. The last thing I'll show is we can zoom in to what happens when we get to the really narrow line widths that would correspond to colder gas. So I'm going to take this exact histogram and just zoom into the narrow line width region. And we find this very steep drop-off, roughly corresponding to a thermal line width of about 1,000 Kelvin, so cool-ish gas. And this is another, I think, really key thing that we can get from synthetic observations and connecting to simulations, because it's really unclear how exactly we should interpret this drop-off. Is it a completeness in terms of our data, the sensitivity that we have? Is it telling us about how well mixed the warm and cold gases are on these scales? Or is it actually telling us something about the true underlying cold neutral medium in these galaxies and how it drops off? That's important for understanding what is the next generation of molecular gas, as this gas is most similar to it in properties. And so it can help us to understand where would be the next generation of molecular clouds, and thereby the next generation of stars forming. And so I'll just leave you with a couple of the questions that I posed here. And I'm now here mostly in person, so I'm very happy to talk to people. So thank you.
Time for a couple questions. I'll let you pick them up.
Oh, is that Vadim? I can't see.
Yeah, so I have a question about the plot that you just showed with PDS. So the distribution of line was very similar for the one and the three, and there was one about these are very different galaxies, right? So I was wondering what do you think about this?
Yeah, this is the part that I'm really confused about, and my concern is that this is a reflection of our underlying data, not actually telling us something about the properties. But it's been hard, and this is really why this part's here. It's very unclear to me exactly how to test this with just the observations, and I think synthetic observations will help a lot to better understand what's actually going on. Yeah.
Okay.
Yeah, nice talk. So you showed a plot showing how you can sustain turbulence within the ISM, like Supernovae and MRI.
Mm-hmm.
Have you also considered like internal feedback processes, so winds and outflows and so on, to help raise that up?
Not in detail,
Okay.
but that's definitely something I'm interested in. And part of that as well is actually using the spatial information that I've sort of thrown away in these plots. So I think we now have the observations to be able to do that, and including some new JWST observations of M33 that'll really be
Yeah, because like for winds at least, compared to the supernovae, the energy injection should be the same, or roughly.
Mm-hmm.
So that could give you a boost, and then you also have outflows. But then you also, like, all feedback will drive, and then it'll give you different solenoidal or compressive modes, right? So
Right.
are you able to sorry, coming from a theorist standpoint, so I'm probably thinking too much about this, but are you able to also from your data get an idea of like the compressive versus solenoidal turbulent driving within these galaxies, or just overall what that is? Because that's something that would be interested for like the simulators.
Yeah,
Their initial conditions.
I think that's going to require making assumption about sort of a three-dimensional disk.
Okay.
But given that we know most of those properties, we might be able to combine it and make some constraints.
Talk more.
Yeah.
I'm curious.
Good. One more? Yeah.
So you showed when you only consider isolated lines that most of the velocities are low,
Mm-hmm.
but there still was this tail to high velocities of like 10 to minus 4. If you believe those are real, do they show interesting spatial structure within the galaxy? Like if you plot where those are?
They are basically everywhere, but they are real. There's some sort of line wing component. My guess is that it's a combination of something to do with feedback. But there's also, M33 has this larger warped disk component. And so it's, I think we're seeing a rotationally lagging component in some parts. So that it's sort of asymmetric. The northern half is blue shifted, the southern half is red shifted, and that's consistent with a sort of puffed up disk that's rotationally lagging. So that's part of what we're seeing.
Okay, thanks, Eric. Yeah, microphone. Yeah. Thanks. So next we have Evan Bauer. Evan is, he studies stars and how they evolve, especially physics of white dwarfs, subdwarfs, stars, binary evolution, and interactions between stars and binaries. He was also one of the developers of the Mesa Stellar Evolution Code that many of us use. Got a PhD at UC Santa Barbara, and then spent some time as a postdoc at JITP before joining us as a CFA fellow. So, Evan.
Great. Thanks. So yeah, I'm here as a CFA fellow right now. I like to think about a lot of things in stellar structure and evolution, but I find white dwarfs to be some of the most exciting things, especially I do a lot of development for sort of physics capabilities for white dwarfs in MESA. So white dwarfs do all kinds of cool things, right? They shred planets, they accrete that material, they tell us what exoplanets are made of. They blow up as supernovae. They'll be great gravitational wave sources for LISA in 10 or 15 years. And the binary physics of their interactions, I think, is really exciting. So that's too much to talk about in a 12-minute luncheon talk. So I'm going to zoom in on one little corner of that, a recent problem that I worked on with Vedant kind of last fall. That was inspired by some of the work he's doing on a specific system that I'll touch on. So one thing that white dwarfs do is they produce runaway stars. I mean really binary white dwarf systems. Because they experience thermonuclear supernovae, you basically end up having one star disappear and release its companion from a slingshot at its orbital velocity, more or less. So in this detailed simulation that I'm showing here, you can imagine having two white dwarfs, sort of in the cave, spinning around each other, right? One blows up as a supernova, the other runs away at its orbital velocity. There can also be a small kick, but I think one misconception you'll hear is that kick is producing the runaway velocity. Mostly it's just coming from the orbital velocity. So that's going to be really important for what I'm going to talk about. And then just a couple definitions. A runaway star is something that's sort of coming from being released by a binary. A hypervelocity star, one definition you'll hear, is something that's moving faster than about 1,000 kilometers per second. So that's quite a fast star. It's unbound from the galaxy. It's going to be leaving the galaxy. And white dwarfs are special because they produce hypervelocity runaways. So I guess I should also say there's more than one way to produce a hypervelocity star. Not all hypervelocities are necessarily runaways from binary systems. But when you see them coming from places that aren't the galactic center, they're probably coming from runaways from binaries. So the other most common way to produce a hypervelocity star is the Hill's mechanism involving a supermassive object like the black hole at the center of our galaxy. But what I'm talking about today is stars that don't point that direction, so they're probably coming from binary systems. So just a couple questions I want to touch on. Sort of these are broadly related to how do thermonuclear supernovae get produced? And the question really is, when we see some of these, are they coming from binary systems that were double white dwarfs that had a thermonuclear supernova? And if so, what kind of interesting constraints can we place on those systems? Because just one big picture question that we still have for things like type 1a supernovae is we don't really know what physics actually produces the detonations and the detailed stellar evolution pathways toward producing things like type 1a supernovae. I often try to use a more general term, thermonuclear supernovae, because some of the predictions that we'll talk about might not necessarily make the classical sort of type 1a in terms of its spectral features, but still involve like an exploding white dwarf. And so, like I mentioned before, this is work I've been doing with Vedant and then a couple other collaborators. Ken Shen does a lot of work in this field, and JJ is just across the river at Boston University. So here are a few objects that were discovered thanks to Gaia a few years ago. This was initially work by Ken Shen and a team that he led, looking for very high proper motion objects in Gaia DR2, looking for things that should correspond to velocities greater than 1,000 kilometers per second. And three candidates, they identified more candidates, but three really stood out as kind of consistently showing the features that they were looking at, or looking for. And these, again, like I said, they don't point back toward the galactic center, so they seem to be good candidates for runaways from binary white dwarf systems. So what I'm showing in this plot is the dashed curves are the sort of velocity posteriors from Gaia DR2. We've had a more recent Gaia data release now, Gaia early data release 3. That's the velocity distributions shown in the solid curve, so those are getting tighter. These candidates are still holding up as really fast runaway stars. But why do I say that these stars had to be white dwarf runaways from double white dwarf systems? And that really comes from sort of Newtonian mechanics in terms of orbital mechanics and the constraints of a Roche lobe geometry. So when you have two stars that spiral inward and start interacting, generically they're going to look something like this. This is a little exaggerated compared to the double white dwarf picture, but you end up with one star, the less tightly bound star is going to start getting more and more tidally distorted until it gets to a point where it starts donating matter onto its companion in this sort of teardrop shape. And that teardrop shape is called the Roche lobe. So this shows the potential in the co-rotating frame for two binary stars. Actually, this would be just two binary point masses. And projected down here, you see some equipotential surfaces. And in particular, there's this thick line near the center of this diagram that's the Roche lobes for the two objects that are in orbit around each other. And that geometry, you can calculate. There's this equation on the bottom right is a rough fit that's good to about 1% for roughly the spherically averaged radius of a Roche filling object. So that's just geometry. It really just depends on the masses and the separations of the two objects. So this parameter Q is the mass ratio of the two things. A is the orbital separation. And then, of course, the other equation, the simple equation I've written down on the left side here is just sort of Newtonian orbital mechanics. So these are two things in a circular orbit around each other. And that pretty nicely constrains the system. So when I go back to this plot and I show these velocity distributions, I can use those equations to translate into an actual radius of an object that's interacting with its companion and filling its Roche lobe. So for one of those objects, that one I'm showing in orange in these velocity distributions, if I translate that into radius space with this equation at the top that I've rearranged just from those two constraints, I kind of get this range of parameters. So I don't get a perfect one-to-one relation because there's a little bit of playing I can do with the masses of the objects. But for things that are sort of on the scale of one solar mass on the x-axis, the radius that you find for that equation for a velocity of about 1,000 kilometers per second comes out to 4 or 5% of the radius of the sun. And then this other object that I'm going to show here is the one that's going about 2,000 kilometers per second. That was its orbital velocity when its companion disappeared. And the radius scales as velocity squared, so that goes down by a factor of 4, and it's less than 1/100th of the radius of the sun. So that's really why we're saying these had to come from double white dwarf systems, is we have this strong geometric constraint on what kind of binary system can produce that orbital velocity. So far this was kind of already known about to order of magnitude, but this work that I was doing with Vedant, we started to be able to constrain this more precisely. And we realized the other constraint that we had to work with for white dwarfs specifically is they have a very specific kind of mass-radius relation. So the sort of simple order of magnitude way to write this down is we know that white dwarfs are held up by electron degeneracy pressure. That gives us an equation of state that I've written down here. The pressure scales as rho to the 5/3 for non-relativistic electrons. Eventually you get to relativistic electrons, and that's rho to the 4/3, but it really just depends on density. And then the second proportionality I've written there is really just what hydrostatic equilibrium gives you for stellar structure. And so together you get a mass-radius relation that looks like radius scaling as m to something like the -1/3, meaning that more massive objects get smaller and smaller for white dwarfs. And so if I make a more massive white dwarf, it will get more compact and be able to fit inside a smaller Roche lobe. So when I go back to this plot, and then I make sort of more detailed models that kind of follow that physics, this is the relation that you get in the black curve for white dwarf radius as a function of mass. And so what we get here, this is the plot that Vedant and I worked out in about a week while we were chatting in the ITC back in September, October. And we kind of immediately realized that this hadn't been written down for these systems before, and there's a meaningful constraint here, so we wrote up a quick paper about it. So what you see is this object that I'm showing in orange, really, it has to be pretty low mass for a white dwarf. It has to be something like 0.2 solar masses, or maybe even less. Whereas this object in blue that's moving twice as fast has to have come from a pretty massive white dwarf that had to get into a very compact orbit to reach its orbital velocity of 2,000 kilometers per second. So if I sort of rearrange this diagram, and I use this relation to map out kind of allowed masses using the white dwarf mass radius relation, allowed masses as a function of orbital velocity. What you see is faster things push up toward much higher white dwarf mass. So this is for the donor star that will be released. There's some range because we think these coming from a thermonuclear supernova means that the accretor star that explodes in the system probably has to be between about 0.85 and 1.1 solar masses to produce a thermonuclear supernova explosion. But you get a reasonable constraint on what kind of masses in double white dwarf systems can produce different velocities. And just one kind of big picture thing to think about when you make a plot like this is what does the average white dwarf look like? So the average white dwarf is 0.6 solar masses. The distribution is very strongly peaked there. And that really would line up with a velocity of something like 1,700 kilometers per second. And the three objects that we know so far don't really line up with that. One is much lower velocity, two are much higher velocity. So that's a little surprising. Just to convince you, this is the white dwarf mass distribution for spectroscopically confirmed DA white dwarfs within about 100 parsecs. So you can see it really is quite strongly peaked there just for individual white dwarfs. So this is at least a little bit surprising that what we're seeing is not lined up with that. Instead, if I take the ones that have fairly narrow velocity posteriors, again, what we see is this D62 orange object is quite low mass. Blue is pushing toward higher mass, and I think this will continue slowly getting better as we get more and more data from Gaia. So these are the main takeaways. There's obviously a lot more detail in the paper that we've now published. That was a pretty quick turnaround in AppJ Letters. So yeah, we can use, I guess the main takeaway I want to emphasize is you can use velocity as a measure of the size of an object in a binary system. And for white dwarfs, there's a really tight relation between that and the mass of the white dwarf. So we can measure the masses of white dwarfs that are running away from these systems. And this introduces interesting puzzles. I think it's just sort of a small piece of what we're trying to figure out with thermonuclear explosions in type 1a supernovae. But it's a fun physics problem, and I think we're starting to get better constraints that will continue to improve. So thanks.
Yeah.
So we actually see these stars, right? Can't we measure their mass and radius from the H alpha and whatever methods people use for?
Yeah, that's a whole part of this that I definitely glossed over. These are very strange stars. They're in a weird part of the HR diagram. They have strange surface compositions that probably are reflecting like lots of debris from the supernova. So they're dominated by things like oxygen and iron and all kinds of elements. So they're probably out of equilibrium in the sense that they were white dwarfs. The things that we see now are puffed up by a factor of 10 compared to that and maybe contracting back down. So their stellar structure is not very well understood, and that's a problem that I want to work on. I intend to work on more, but it's a pretty difficult problem.
I see. So there is no easy way of just directly measuring mass and radius.
Right, yeah. In isolation, they're just sort of running away. I guess we do have a radius constraint on the current star, but there's no way to map that to a mass. Turn.
So these runaway stars are the stars donating onto the white dwarf that will explode, right?
Right, yeah. In this scenario that I've mapped out, the less massive white dwarf is a little more puffy. That's the one that becomes the donor. The more massive white dwarf explodes as a supernova and disappears. But yeah, the runaways are the donor stars.
Is it a significant amount of mass that the donor donates to trigger the companion to go supernova, and could that shift like the typical distribution away from the like the peak at 0.6 solar masses per white dwarf?
The thought in the scenario for these systems is that the explosion happens pretty promptly. It's triggered by the helium that's being transferred rather than the so most of the white dwarf donor is carbon oxygen. It has sort of 1% of its mass as a helium envelope. And that's the stuff that, as it's getting transferred, causes a detonation that then travels into the center, the core of the accretor white dwarf, and causes the entire thing to become a supernova.
Yes, I remember the orange one is the one that traces back to the center of the supernova.
Right, yeah.
So you have the age. What do you think is the time scale for readjusting to an equilibrium structure?
Yeah, so I think the time scale for tracing back to the supernova remnant is pretty short. It's, what, 10,000 years? Yeah, so a few tens of thousands of years. I would say the only other time scale that we know very securely is the Kelvin-Helmholtz time scale, because we have a luminosity and a radius. And that's more like 1 million to between 1 and 10 million years. So the sort of thermal readjustment time scale is very long compared to what we think might be, the age of this runaway star, which is why I think it's probably pretty far out of equilibrium and hard to understand its structure. Jesse?
Well, thank you, Evan. So before we end, let me just advertise, we will have Cora Dworkin speaking this afternoon at 4 for the closure. She's here right now. Hi, Cora. I think our dinner table is full, but if you would like to speak with her, there's still some time slots available, and you have an email in your inbox about that. So yeah, let's just conclude by I want to express my delight at seeing so many people here, and thanks to Avi for approving of the funding for the sandwiches that we will have starting 2 weeks from now. And thanks to Daniel for encouraging us to be physically present here. Thanks to Sarah and Jamie for arranging the talks, and to our speakers for giving excellent, edifying, entertaining talks with the right number of references to Monty Python. And thanks especially to all of you for coming. See you at 4 o'clock.
Yeah, I remember the radius. It's inflated back there.
Of course, the speaker there, she's